In this unit, we're going to be looking at finding the derivatives of log functions, exponential functions, sine and cosine functions. Today we're going to start looking at the derivative of a log function. Before we do, we need to review a few things from Pre-Calc 30. First, remember the relationship log base b of x equals y, then base b to the power of y has to equal x. When you're asked to evaluate a log, you're looking for an exponent. For example, evaluate log base 5 of the cubed root of 25. 5 to the power of what? We're looking for an exponent, has to equal the cubed root of 25. Now this question mark that we're looking for, we can use a variable to represent, let's say y. I'm also going to change 25 to base 5 since I'm working in base 5, and change the cubed root to the exponent 1/3. 5 to the power of y has to equal, remember when you have a power raised to a power, you multiply the exponents together. We can clearly see that y will have to equal 2/3, which means log base 5 of the cubed root of 25 is equal to 2/3. A few other things to refresh your memories with. If no base is given, you conclude that you're working in base 10. Remember, this is what our calculators can do. Some basic graphs of log functions. For example, I have log base 2 of x here. If your base is greater than 1, then your log function will be increasing. If your base is between 0 and 1, such as 1/2, your log function will be decreasing. All log functions go through the point 1, 0. Here I have a y value of 0 and an x value of 1. Changing formats, b representing any base to the power of 0 has to equal the x value. I know anything to the power of 0 is 1, 1 equals x. That's why all log functions go through the point 1, 0. Furthermore, product property, log base b of x times y can be expanded log base b of x plus log base b of y. Similarly, the quotient property, log base b of x over y is equal to log base b of x minus log base b of y. Finally, your power property, this exponent n can be dropped out front. Log base b of x to the power of n is the same thing as n times log base b of x. These properties will come in handy when we're finding the derivatives. In order to find the derivative of this log function in general, y equals log base b of x, we need to explore the origin of e. E is a special number. Just like we know pi to be approximately 3.14, e is approximately 2.718. Let's look at how this number came to be. E is defined as the limit as k approaches 0 of 1 plus k, all to the power of 1 over k. So I'm going to start at a k value of 1, and I'm going to get closer and closer to 0. We won't do all of these, but we'll do most of them. Replacing k with 1, 1 plus 1 to the power of 1 over 1 is the same as 2 to the power of 1, which is just 2. K value of 0.1, we're going to have 1 plus 0.1, which is 1.1 to the power of 1 over 0.1. 1 divided by 0.1 is 10. 1.1 to the power of 10 gives us 2.5937. I'm going to continue to do the same thing with these k values as they approach 0. Now we can already see that as k gets closer and closer to 0, 1 plus k to the power of 1 over k gets closer and closer to 2.71828. Now this decimal will go on forever and ever, will not terminate, will not repeat. We're going to approximate e as 2.71828. You should remember that. We're going to develop the derivative for y equals log base b of x. The derivative is equal to 1 over x log base b of e. We're going to use this general form of the derivative for log base b of x to find other derivatives, such as log base 4 of x to the power of 10. Before we do that, I want you to know where this derivative originates from. Remember our definition of derivative here, applying that to the function log base b of x. We're going to have the limit as h approaches 0 of log base b of x plus h minus log base b of x all over h. Using the quotient property, rewriting this log statement as log base b of x plus h all over x. And that's all over h, taking the limit as h approaches 0. Just writing the 1 over h out front instead. Next step, I'm just rewriting this here as x over x plus h over x. X over x is 1. Now I'm going to multiply this by x over x. And I'm just doing this to get to where we need to be in our proof. By the way, it is not necessary to know this proof for the test, but again, I think it's important that you know where this derivative originated from. Now I'm going to rewrite this as 1 over x times x over h. I'm just changing the position. After all, I'm still multiplying by x over x, which is just 1, so I'm not changing the limit. Next, I'm going to let k equal h over x, as we can see here. Next, applying the power property, I can rewrite this as the x plus h, put in the exponent spot. Now, since k equals h over x, then I can conclude that 1 over k would have to equal x over h. Therefore, this x over h becomes 1 over k. Notice we're getting closer and closer to getting what we need. Since h is approaching 0, then k would also have to be approaching 0. Now, taking the limit as k approaches 0 of 1 plus k, all to the power of 1 over k, will be e, just like we learned here. Therefore, we'll be left with 1 over x times log base b of e. Therefore, in general, the derivative of y equals log base b of x is equal to 1 over x times the log base b of e. You will need to memorize this. Let's use this knowledge to find the derivative of these functions. dy dx is equal to 1 over x, I'm just following this format, log base 6 of e. Done. Here, dy dx is equal to, still following the pattern, instead of 1 over x in our derivative, we're going to have 1 over x to the power of 10 times log base 4 in our case of e. Now we have to use the chain rule. We have to take the derivative of x to the power of 10. So times 10 x to the power of 9. Let's see what we can reduce. X to the power of 9 over x to the power of 10. We're left with 10 log base 4 of e all over x to the power of 1. Next, dy dx is equal to, this 12 is just a coefficient out front, so it can stay out front. Following this format, we're going to have 1 over x, but in our case, 1 over x cubed plus 4x, log base 7 of e. Now, again, chain rule, finding the derivative of what's inside, times 3x squared plus 4. And writing this nice and neat, we're going to have 12 log base 7 of e times 3x squared plus 4 all over x cubed plus 4x. Now, if you could factor anything and reduce more, of course you would. Example 2, find the slope of the tangent line to this curve. And this curve is a log function. We know the derivative is the slope of the tangent line. F prime of x is equal to 1 over x times the log base 2 of e. Now specifically, I can find the derivative at x equals 3 by substituting in 3 for x. Remember, our calculators can only evaluate logs in base 10. Here we have base 2. But good news, there's something called change of base formula. And this is something new that you did not learn in pre-calculus 30. Here's how it works. Log base b of x is equal to log of some other base, we'll call it a, of x all over the log of the same base of b. In our case, if we want to use our calculators, we will want the base a here to be base 10. Let's look at this quick example to get some practice. Log base 10 of 6 over log base 10 of b, which in our case is 3. Now, if you punch in log of 6 on your calculator divided by log of 3, you will get 1.6309. Now let's go back up here and change the base. Log base 10 of e over log base 10 of 2. There is an e button on your calculator. Just like we have a pi button on our calculator, we also have an e button. See if you can find it. It's probably a second function. Here's what I want you to punch in. Log and then e divided by, now you may have to use brackets when you're entering the bottom here into your calculator. Bracket 3 times and then log of 2. Now you will get an answer of 0.48090. Please keep around 5 decimal places in your answers. There is something called natural logarithm. Natural logs are special logarithms, and what makes them special is the fact that the base of the log is e. The notation for natural log is ln x. The natural log of x is equal to log base e of x. As soon as you see this notation, you should think base e. We need to know how to find the derivative of natural logarithms. Let's say we have a function equal to the natural log of x, in other words, log base e of x. Then the derivative would be equal to, and just following the format for the derivative of a log function, 1 over x times log base e of e. Now, let's look at log base e of e. It's equal to 1. Here's why. If we evaluate log base e of e, we want to know e to the power of what is equal to e. Well, we can clearly see it's 1. Therefore, if our function is the natural log of x, then the derivative is just 1 over x, since the log base e of e is 1. Let's get some practice. Find the slope of the tangent line to the graph of f of x is equal to the natural log of x, where x equals 2. We're finding the derivative. I know the derivative of the natural log of x is 1 over x. Finding the derivative at x equals 2, subbing in 2, we have 1/2. That was easy. Question 4, find the derivative of the following functions. Okay, we have natural log as our function. This 9 is just out front. F prime of x is equal to 9 times, instead of 1 over x, we're going to have 1 over 3x minus 5. And then finding the derivative of what's inside using the chain rule times 3. And you get 27 over 3x minus 5. There's your derivative. Last question, save the easiest for last. The derivative of the natural log of 2. The natural log of 2 is a constant. Notice there is no x value listed anywhere. We know the derivative of a constant is equal to 0. That's all I have for you today. Please work on this assignment. You will need to remember these 3 things. Please keep them in front of you as you work through the assignment, remembering the derivative for log function, derivative for natural log. This concludes our first lesson on finding the derivative of log functions.